because that 12 volts is still stuck right there. The distance between them, I could also change if I change the gap between them, if I cut that in half, I would have doubled my electric field. And doubling the electric field would have ultimately doubled my density here, which ultimately would have doubled that. So I could have done something there, I could have just changed the width there. And that's part of what you did when you changed the distance between the plates in the lab.
Don't we double the area to increase the charge?
All right, so, not double the area, you cut the area in half.
Oh.
Did I say double the area? You said cut it, make it smaller.
Yeah, you said cut it in half.
Yeah, this would be cut in half.
But isn't
Hold
Q equal sigma times?
It is not cut in half, sorry.
It's
You're right.
double.
You would double the area. Because Q is the area times that. So it should be twice, thank you. All right, are you good with that? Sal? Yeah, sorry, I didn't catch it earlier.
So was that not just a double Q?
Yeah, just a double Q.
So that's the charge of the positive plate?
Yes, that's the charge of the positive plate, and then the negative of that is the charge of the negative plate. So if we think about the amount of charge that's being held on these plates, obviously the more charge you hold in these plates, the more you can do with it. So for example, if you've got a camera with a flash, you want a very quick dump of current going through the light bulb to get it to flash. So you have a capacitor that's all charged up. And so when the flash is enacted, you basically connect the two. You got charge stored there. You have a light bulb with a disconnection. You make the connection, all of a sudden, all the negative charges, all the electrons are going to start flowing across that bulb. It's going to get very bright very quick as the plate discharges. So a flash is one way of doing it. Another place for it are tasers, stun guns. You have a lot of charge stored up and you want to dump it very quickly. And it's a personal question, so you don't have to answer. Anyone here actually been hit by a taser or stun gun?
No, but I want to.
My first year here, I had a student who had gotten tased before. Former Marine. He said he peed all over himself. So I'm not quite sure that's an experience that I want, but you be you.
Is that like an initiation?
I don't know. He didn't actually go into much detail about why he got tased.
I think I've seen that before.
Yeah, I've seen it on
like
TikTok,
cops
I
or
think.
something had to do it.
Yeah, I thought it was like our police training to get, you had to get shot by a taser.
Okay.
Yeah, I'm sure it's part of their basic, cause they even have to go through like gas chambers and stuff.
So do they have to like resist it?
No, so
No.
basically
It's just so you
stand
know
there.
what's going on.
Like they have a mat laid down and you're standing there and they have two people ready to hold on to you and they like shoot you in the back or something, as far as I know.
I don't know
You just
why.
have to
So yeah,
experience.
what benefit does that?
It's basically so you know
Yeah, for
what
like-
the experience is.
Yeah, for a police
Before
officer
you
to
do
carry a
that sometimes.
taser, they have to be shot by one before they can carry one.
Which makes sense.
Oh.
But the same isn't true for guns, so.
In order to use a gun.
If it was, you'd have a lot less people wanting to get guns.
I mean, you can do a simulation, I guess, of the ping.
I guess that's where all the airsoft guns go.
I was just suddenly, I took your suggestion and went with it and just wondered, all right, suppose you did have to be shot before you could carry a gun.
Where would you get shot?
Yeah, that's what I was wondering.
In the shoulder.
You get to choose. You get to choose.
It's like in the leg. I want to carry a gun, but I don't need to walk for that.
But then you'd identify, you see a police officer with a limp, you go, oh, he's got a gun. All right. Now, we are storing a certain amount of charge on the plates here based upon the amount of voltage. If I change the voltage, that also would do it. If I doubled my voltage, then my electric field gets doubled, which means that my current density gets doubled, which ultimately would double my charge. But this ratio of the amount of charge that is held divided by the voltage across the plates has a special name. This is capacitance. And is represented by an uppercase C, which also represents coulombs. Please be aware that I have two different C's on the board here. I've got this C right here and this C right here. They do not mean the same thing. Typically, you can tell that coulomb comes after a number, capacitance usually doesn't. So the capacitance of this particular capacitor over there is equal to my charge, 1.062 times 10 to the negative 9 coulombs, divided by the voltage of 12 volts. It's going to be what? 9 point something times 10 to the negative 11.
8.85.
8 point what?
85.
Oh, okay. And now the units. We have coulombs per volt, but it'd really be nice not to have a capital C on both sides of the equation, meaning two different things. And so they also wanted to honor somebody, and that is the farad.
So the SI unit of capacitance is a farad?
Yes. Named after?
Faraday.
Yes. It's one of the few units where they just took part of the name off to honor Volta. Volt was also named after Volta.
So the bottom one's still supposed to be to the negative 11?
Oh, yes, thank you. And I still wonder about going through all the videos, if I have to watch my videos and then thought, wow, there's a mistake there, and there's one there. How many would I find? All right, so I have a formula. So the formulas I'm working with here, I have capacitance is Q over delta V. I know that delta V is negative E dot delta X. Or if I'm just looking at magnitudes here, that the magnitude of my voltage is just equal to the magnitude of my electric field times the distance between them. The VET or VEX equation. I have that my electric field magnitude is sigma over epsilon sub naught, which is Q over A over epsilon sub naught, which is just Q over A epsilon sub naught. I've left any of them off yet. That pretty much sums it up. So let's sort of combine some of these equations. So my electric field is equal to this, so I can plug it into my second equation there. So my voltage is going to be equal to Q over A epsilon sub naught times D. Rearranging this equation, I'm bringing delta V to the denominator on the right and moving everything but Q over to the left, so I get A epsilon sub naught over D is equal to Q over delta V, which is equal to my capacitance. So now I have an equation for figuring out my capacitance of my parallel plate capacitor, like in the lab, just based upon the area, the permittivity, and the distance between them. Now there is one thing missing in order to really connect it to the lab more fully. Questions before we add in the last little bit for capacitors? Then let's add in the last little bit, the dielectric. I got my positive plate here, I got my negative plate there. We have so far assumed that there's basically air or free space in between, but now we're going to add a dielectric, we're going to add some material in between. The permittivity of the dielectric is not the same as the permittivity of free space. Epsilon is equal to the permittivity of some material, of a medium. And so free space here, this is 8.85 times 10 to the negative 12 in SI units. This might be 16 times 10 to the negative 12 in SI units. Or 32, or some number bigger than 8.85. Now, instead of trying to remember the permittivity, some scientific notation permittivity for all different materials, they decided to go for a shortcut. And if you take the permittivity of the material divided by the minimum map value, this is a kappa. It is not a K, it's a kappa. And this is known as the dielectric constant. Kappa is what you're finding in the lab. It should be bigger than 1. But some students, again, in the effort for getting Nobel Prizes, have come up with kappas that are not. Sometimes it's because they didn't take their slope out to that extra decimal place. So my equations over there, everywhere that you see epsilons of naught, we can just drop the naught. And so capacitance for a parallel plate capacitor is A times epsilon over D, which is just A times kappa epsilon sub naught over D, since that's what epsilon is. Or traditionally kappa is written first. So that is the relationship that you're exploring in the lab, or exploiting, whichever one you happen to be doing. So if you are plotting circumference versus 1 over the distance, then, not circumference, capacitance versus 1 over the distance, then you get C is equal to kappa A epsilon sub naught times 1 over D plus 0 if you want to get into y equals slope x plus b form. And so there's my slope, and that's my ideal intercept right there. Or, if you're plotting capacitance versus area, then we have kappa epsilon sub naught over the distance times my area plus 0, and there's my slope, and there's my intercept, ideally. But once you have the slope, you can then solve for kappa, because area, the overlapping area was constant here, epsilon sub naught's a constant, and over here, the distance between was a constant for that last part. And epsilon sub naught is a constant. All right, questions to here? So let's take a look at our equations over here. When we put actually, do one thing first. When we put the dielectric in here, I have an electric field coming from the plates that is going from the positive to the negative plate. Dielectrics are insulators, so we're not going to have charge flow, but we'll have electrons shifting. And we've talked about that. We basically are going to create a dipole in here. And so we're going to have a bunch of little, the electrons will move closer to that. They're still bound to the nucleus, but we're going to get a whole bunch of dipoles in the dielectric. And the electric field here for all these tiny little dipoles goes from positive to negative. So I have this back electric field. An electric field that is opposing the external electric field. So that will make the electric field in between smaller. So this E is going to get smaller. And which will make the voltage smaller. Well, depends on other things, but for right now, we'll just pretend that it's a capacitor just sitting there. So as E gets smaller, my voltage will get smaller, assuming the distance stays the same. As the voltage gets smaller, my capacitance increases. So when you actually make a capacitor, if I took two pieces of aluminum foil, I put some dielectric in between them, which means some insulating material, paper, wax paper, something that's not going to conduct, and then I roll it up as tight as I can. The dielectric actually serves two purposes. One, it keeps the two metal sheets from touching each other, thus shorting out the capacitor. And two, it provides basically a greater capacitance overall. And that's in essence how most capacitors are made, is you take two sheets of metal, put some dielectric in between them, and you roll it up tightly. There are far more sophisticated capacitors that do it differently, but that's the essence of the ones we deal with. So let's take a look at our equations. I have two electric fields here. I have an electric field coming from the plates themselves. So my electric field from the plates is still equal to the sigma over epsilon sub naught. Because I have some charge there, it assumes, and the electric field coming from it just ignores the dielectric. The total electric field, so once I bring in the fact that I've got an electric field coming backwards, the total electric field is equal to sigma over epsilon, which is sigma over kappa epsilon sub naught. My Vex equation here, this E is the total. Recognize also my capacitance is equal to kappa A epsilon sub naught over D. Well, A epsilon naught over D is the capacitance with nothing in between. And so if I represent this by C sub 0, just as sort of that bare capacitance, then for a parallel plate, this is also equal to kappa times C sub 0. So dielectric increases the overall capacitance.
And you said, I don't know if that 16 times 10 to the negative 12, is that the value of just epsilon?
Yeah, I'm just making, it differs from material to material. I said, I was just giving an example of something that could be. you here. So recognize, I now have one more way of actually adjusting the capacitor in order to, say, double the charge on it. I can also put in a dielectric in. So let's do a little manipulation there. Actually, I am going to do. How much for preview do you want of the lab you're doing on Thursday? I can continue on the roll I've got here for another 10 minutes, or I can take 10 minutes out and sort of talk about the lab. Do you care?
Just talk about the lab.
Yeah, that's helpful, yeah.
So I've got two really long plates here, hooked to a battery. These plates have some size to them. There's some distance between them. You can, if I gave you that information, you could calculate what the capacitance is. I'm going to change the configuration just a little bit here. This wire right here, I'm going to split. So I now have that wire connected to two parts of the plate. Is that going to change anything fundamental about the capacitance? Will it change the voltage across the plates, or will it change the charge on the plates? I got one said no, and a couple other just doing the staring. I got another one saying, got three going no, got four. I'm going to go with what you were doing just then, Kyle, as a no. All right, it shouldn't change it. All it does is just change how the electrons are getting on there, but once they get to the plate, they'll spread out. And now, I'm going to basically cut the plates perfectly, so I'm not losing any material. I cut the plates in two, but so it's still the same total amount of area, just now there are just two of them there. Does that change the overall, how much charge I can store on the plates? Not on each individual plate, but the total charge from both plates. Got a couple people shaking their head no. And then a sideways one, but we'll go with, it doesn't. So I could treat this as two capacitors, or I could treat it as just one giant capacitor. So if the electrons move along and then they have a choice of going one way or the other, and then over here they could join up again on that side, this is known as parallel. These are parallel capacitors. My total capacitance for parallel capacitors would just be, well, it's the capacitance of one plus the capacitance of the other one. If we think about it in terms of total charge over the voltage, this would be, I'm going to write down EQ for equivalent. The voltage is the same because, again, it's path independent. Whether I go this way or whether I go that way, whatever I gain in potential here, I have to lose the potential going across either side of these. So my potential is the same, so that's going to be charge of one, the charge that's on one capacitor over the voltage plus the charge on the other capacitor over the voltage. And so what we end up with is that the total charge is just the charge on one plus the charge on the other. Generally, the derivation is done in the opposite direction. But equivalent capacitance for capacitors in parallel is just you add them up. So if I have a 3 microfarad capacitor here, and a 4 millifarad capacitor there, what's the equivalent of the total capacitance? Yeah. That's my equivalent capacitance. So some of the lab that you'll be doing on Thursday is you'll be putting capacitors in parallel and checking this out. Now, if I have what are called series capacitors. So capacitor 1, capacitor 2. If I hook it up to a battery, I get an electron popping on here, and then it chases one off of that plate, and puts one there, and chases one off that plate. Then I put another one here, chase one off, put another one here, chase one off. In other words, if these connected, there's only one path for the current to flow, that's series. So over there, the voltage was the same across both, but over here, it's the charge that's the same across both. So my equivalent capacitance for this combination should be equal to Q over delta V. If I think about the voltage here, I gain potential going across the battery here. I'm going to lose some going across this one. I'm going to lose some going across that one. So the voltage across the battery is equal to the voltage across capacitor 1 plus the voltage across capacitor 2. If I solve for delta V in this equation right here, I get Q over the equivalent capacitance is equal to Q over capacitor 1 plus Q over capacitor 2. All the Q's are the same for the reason outlined here. And so in the case of series capacitors, 1 over the equivalent capacitance is equal to 1 over capacitor 1 plus 1 over capacitor 2. So if I had a 3 millifarad capacitor and a 4 millifarad capacitor, what is my equivalent capacitance? What?
1.71.
Is it 7/12?
And then 7/12 is if you added these, but don't forget, that's the reciprocal of the equivalent.
That's 12/7.
12/7. Millifarads. So it reduces the overall capacitance. Now, why would you want to? Well, it depends on what you're designing. Sometimes you want to put a safeguard in there so that it doesn't get you aren't storing too much charge. It's all about trying to control the current flow. And so, in essence, part of what you'll be doing is you'll have capacitors in series, and you'll check to make sure that that comes out with the equivalent capacitance. And then you will do one where you've got series and parallel. And then I think you'll do one where you're shooting for a target and you'll use however many capacitors you need to in order to get the target. But on that note, have a safe couple days.